Okay, so let's start with a story. Let's jump back to 2014. We'll go to North Carolina. There's a woman named Brisha Borden. She is late to pick up her godchild at school. She, on the way there, she's been late a couple of times recently. There's risk that her godchild will end up in a gang if she doesn't get there in time to pick him up based upon the social dynamics in the area where she lives. So she looks to her sides and she sees that there's a Huffy bicycle and a Razor scooter with a friend of hers, and makes a quick judgment call in her mind that it's worthwhile to steal the Huffy bicycle so that she can go and pick up her godchild on time. She gets caught, she's seen, and the police come and they use a tool to assess her risk, and she comes up as an 8. Okay. Same day, I think it's in Illinois, a man named Vernon Prater walks into a convenience store armed and does the standard armed robbery gig, takes a lot of things from the convenience store, gets caught. The same tool that was used to assess the risk of Brisha Borden is used for Vernon Prater. Vernon comes up as a 3. I didn't include 2 details in these stories. Vernon is white, Brisha is black. Brisha is a woman, Vernon is a man. So this is their respective scores. This is what they look like. These scores are supposed to predict the future risk, should these people go to jail, get some sort of sentence, the risk that they will commit a crime again in the future based upon that sentence. So she has a pretty high score. So this tool is telling us that we should give her a relatively long sentence because it's highly likely that she's going to do something really bad in the future. And the low score means even though this guy did a bad thing like go into a convenience store and try to rob it with a gun, it's highly unlikely that he's going to do something bad in the future. So how did the tool do? So in the future, Brisha, who did have 4 prior offenses, had 0 subsequent offenses, although she was rated quite high. And Vernon ended up having 1 grand theft offense. And if we look in the past, he'd had 2 armed robberies, not just 1, and 1 attempted armed robbery. These are the things that he was caught for. So it's possible that Brisha indeed did many other things in the future. He just wasn't caught, and that Vernon wasn't lucky and he did get caught. It's possible. These things are hard to measure. So then we say, all right, is this just an anomaly or does this happen often? And if we look at the data, black defendants' risk scores tend to be relatively high across the board. And white people tend to have mostly low risk scores. And if you note, the histogram sort of becomes, there's very few white people that have high risk scores. It's relatively high on the black side. So why is this happening, right? What's going on here? So if we think about the discourse in the press related to ethical algorithms and their risks to society, there's certain people who say these things are evil, right? They're going to take over the world, and there's existential risk, in particular when the algorithms get smarter than we are. There's many other people who say that they just think so much differently than we do, right? So when algorithms are used to make judgments about whether or not somebody the length of the sentence they should receive, whether or not we're here at Capital One, do they deserve a loan? Do they deserve a credit card? How high should that be? They say they think differently than people, they think better. I think neither of those 2 answers are all that practical. I would like to argue today that algorithms are best viewed as convex mirrors that refract our own biases in society, and that is actually an opportunity. We might be facing a time where for the first time we actually have quantitative evidence of how we actually work as opposed to how we think we'd like to work in society. And that if we're careful and thoughtful about how we build and deploy these algorithms, we might have a chance to do to use them and tweak the math so as to design sort of the outcomes we'd like as opposed to inherit the past we can't help but have. So what I'm going to do over the next hour is explain to you sort of how this all works technically and why it comes up in the first place. Go through sort of the greatest hits in bias. There's a lot of examples there, but I'm trying to span various areas within which bias and judgments can enter into algorithms. It's not just about like the algorithm itself, it's about the whole machine learning product development process. And then the last thing is what can we do? So what can we do technically? What can we do from a policy perspective? What can we do socially to try to design the future we want as opposed to irresponsibly inherit the past that we have. Okay, so why is this the case? All right, so let's level set for those in the audience who aren't working actively in AI, sort of what this is and what this all means. So I used to work at a company called Fast Forward Labs. Really love my colleague Hilary Mason's Maslow's hierarchy of data science capabilities, where AI sits at the top, and basically everything starts with this foundation of data. Big data is an misused term, but it means our ability to collect, store, and process data at scale so that we can do stuff with it. So what are the things that we want to do? Well, we want to be able to count things, right? We want to be able to add, subtract, multiply, and divide, know things about the past, so that we can sort of get a sense of our grounding in the world. And then we might get more complex and start to model functions on data, right? So data science is applying math to data so that we can predict what might happen in the future based upon trends within the past. And the things we might predict might be sort of linear. So y equals mx plus b is the favorite equation that we all remember from high school, where we just start to make functions that look like this. We make predictions in the future, or they can be super complex, right? And when we think about deep learning, which is a term I'm sure many people have heard if you're working in AI, basically we go from let's model this to let's model this, not in the 2 or 3 dimensions that we're all comfortable in, but 50 million dimensions, right? So the amount of complexity that we can capture from our data sets exceeds our ability to sort of comprehend that in our minds. But it basically is just linear algebra and math in multiple dimensions. When you get machine learning, we sort of are using data to shift our slope over time, right? So it's easy for us to vision that linearly, right? The more data we get, we sort of move our slope up and down. But when we get to these 50 million dimensions, that gets pretty tough. And then AI is, what we all call this stuff. So in terms of what's going on in ethics, for me, this slide may be the most important slide in the deck. There's a couple of others that I'll pick out. So if we think back to that initial anecdote with Brisha versus Vernon, it's not news to anybody in this room that African American males tend to be incarcerated more frequently than Caucasian females, right? This is not something that society doesn't know about, and there has not been sociological analysis for a long time. So distributions and using data to study society is certainly not new. What's a little bit newer and starting to really impact things is that we're taking what was once passive, we're simplifying it into an action within a product. So we take sort of this distribution of probabilities, might Brisha commit a crime in the future, we're representing it as some score to make it tractable and interpretable for a human user and to gauge an action. And then we act on that score, and we're changing the distributions based on the output of those actions, because there's that feedback loop. So this shift from what was once observed passive analysis that could maybe inform an affirmative action program into something that is automated. Sometimes it's a user, it's supporting a decision. Sometimes it's just brute force automation and happens at scale and has feedback loops that then impact people's perceptions of themselves and goes back to change the product. This is really why we're here today. And I'll talk through various instances. What I won't talk about is sort of fake news and filters and algorithmic bias on Facebook. But that phenomenon is quite similar, and how we engage with this content shifts then the content that's sent back to us, and it becomes this feedback loop that really is able to exacerbate and amplify social trends and biases at scale. All of this is powered by fundamentally a particular type of machine learning. So when you hear about machine learning in the media, you hear that machines are magical beings that can find patterns in data. And those patterns take mess, and they sort it into nice, fancy clumps in ways that evade our human measly minds. That is an active area of research within the machine learning community. It's used often for data exploration, but very infrequently shows up in real-world products out in the world. So this is a clip from Andrew Ng's HBR article about supervised learning. I show it not to sort of go through all these applications, but just to say that it's an example of somebody saying that 90% of the machine learning products that are out there use a different type of machine learning called supervised learning, which I like to think about as follows. So in supervised learning, we want to know something about the world that's really hard to know, where hard to know is hard to measure. And to do that, we find a proxy that's much easier to know. And then we can find a function, a mathematical expression that defines a correlation between the easy to know thing and the hard to know thing. And we use this function to make guesses about the hard to know thing in the future. Sorry, the format's a little off because I use Keynote and we had to change it over to PowerPoint. So let's give some examples. I just moved to Toronto last year. People up there complain about how expensive the housing market is. There's some folks here I know from San Francisco. For us from like New Yorkers and San Franciscans, it's kind of laughable. I pay like a third of what I paid in New York for my apartment in Toronto. Actually wrote in once when I moved up there, we did a cost of living comparison between potentially my going to San Francisco or here, and I would have had to make like 3 times as much money to take a job in San Francisco as I do in Toronto with the same standard of living. So great place, and go work at Capital One, come work in Toronto, it's great. So problem at hand, I'm moving to Toronto and I want to know how much is reasonable for my housing. But that's a hard thing to know because I'm not a real estate agent. What I can do is go buy a tape measure and do a little bit of analysis and realize that the size of my apartment is the thing that is most tightly correlated with price. So if I want to know price, a good proxy is to just go and measure the size. It could have been, it's got a nice washer and dryer, it could have been what neighborhood it's in. There's all sorts of things we might consider relevant to make this prediction. But I did some analysis, I determined its size, and then I go out and I ask my friends, hey, how big is your apartment and how much are you paying? Okay, and I plot a bunch of those examples, known data sets. We call that labeled data when we know what the right answer is. And then all I do is I go in and I put in my size, and then I ask my regression algorithm, how much should I price? And it says, you should price it at $1,500 per month. And you're like, are you kidding me? That's for like a 1-bedroom in Toronto? So for real. And then we say, and we won't talk about bias until later. So that's machine learning, right? That's an example of building a supervised learning regression algorithm to try to predict price from some variable. Often our data sets they don't fall in these nice like continuous patterns. They'll be in clumps. So a classic example is spam. Is this email spam or not? So we do the same process. We say, I don't know, that's hard to know if it's spam. But it's really easy for me to see if the word Nigerian prince has shown up in my email, right? So you say, all right, if it's Nigerian prince, it's in the spam bucket. If it's not, it's in the non-spam bucket. Then you're going to say, well, that sucks. This is like a shitty classifier. It's making so many mistakes. So you may say, well, I don't know, let's add spelling mistakes. Let's add weird metadata, right? There you can think about all of this list of things that would make something spam. And as we go from, basic types of machine learning algorithms to more complex, we're adding in those features, pushing them out in more dimensional spaces to make that distinguishing line ever more accurate and concrete. Note, however, we humans are sort of making the judgment calls on what might matter and not. So when we shift into a problem like this, we're like, okay, I want to know which is a cat and which is a dog, but I don't know which P is the right P. So is it like the shape of the eyes, the ears, the texture of the photo, right? What features in that image, in those images, are the ones that matter? So deep learning is the variation on the theme here, a set of techniques where we say, well, it's gotten so hard, let's use processing to help the computers figure out what matter on their own. So these layers of computing, basically, they're going to make a representation, and at each layer, they're subsequently processing it so that they can build out complex concepts from sort of these basic features. And the key thing for our purposes here is that we compose the layers, so we sort of architect how the network works, as opposed to going in and deciding which features matter. So as opposed to going in and saying it's the price, it's the square footage, or it's Nigerian prince, we allow the computer to sort of figure that out ourselves. There's more to deep learning than this, but it helps to give an intuition that it's not like a radically different form of machine learning. It's a more complex extension of existing paradigms and processes that we can more easily understand. So when you have your data, I really love this slide. My friend Graham Taylor, who's a professor in the University of Guelph in Ontario, drew my attention to this. It's very important. How we end up representing our data can strongly determine the performance of our algorithms. So if we take, going back to our spam classifier, we want to put things in bucket A and bucket B, we may have represented our data in like a Cartesian plane, and it looks like that. And we're like, God, I don't know where to put the line that divides things. If we put it in polar coordinates, so things that are sort of more centered right around a different axis, suddenly the problem becomes tractable. Super important in terms of how we use various algorithms to represent our data. So the corollary of going into deep learning is that when we stop selecting which features matter, it becomes harder and harder for us to know why the system does what it does. So more intractable for us to be able to say, oh, it was that square footage that led to the output. So they start to make decisions where we're like, when we go back in and we want to say, why didn't Miriam get a loan? The system's like 0.88% accuracy, right? So they become more impenetrable and intangible as they get more complex, which has issues for, corollaries for this issues. Questions on that before I go on? Okay, cool. Okay, so basics, supervised learning, this is how these products work. It's math. So where does bias creep into this equation? So if we go, just as a basic thing before we go deep, we had this thought with deep learning that when the humans come out, so we're not picking out the features as much, the model's less explainable. And there's a lot of people in the machine learning community who say, well, there's not that much bias in these like more logistical algorithms or decision trees or those that feel more tractable, and they're much more explainable. So sure, they are explainable, but they're not immune from bias for that reason. So this ProPublica example that I gave at the beginning, the compass recidivism algorithm as reported by ProPublica, they were using a logistic regression algorithm. So something that's like quite similar to that first example of is it spam, is it not spam? They're not using fancy deep learning. They're not using things that are like very, very technically black boxes. They're using something that should be explainable, but there's still bias that can come into the process of picking out which features matter in the first place. All right, let's break this down even more tactically. So this is I'm not going to talk about this slide. It could take a long time. But when we build a product using an algorithm, it's not just the algorithm. There's a lot more to AI than meets the equation. So what I'm going to do for the next section is talk about where bias can enter into the picture at the various phases in this machine learning product development process. So a key initial question that I take from Jonathan Zunger, who wrote an article about this recently on Medium, is that when you're designing these proxies, these good representations for the hard things in the world that you'd like to know, there can sometimes be a gap between the thing you really want to know and the thing you're actually able to know and measure. When these differ, your model is going to be really great at predicting the quantity you measured and not the quantity for which it was meant to be a proxy. So Junger actually uses this. The example that stimulated his comment was the first example that I gave in the talk, where he said, what we think we're asking is, what's the probability that Brisha will commit a serious crime in the future as a function of the sentence you give them now? So what the judge wants to do is say, I have to make a decision as to whether or not I put Brisha in jail for 6 months or for 5 years. And I will only do the 5-year sentence if that will actually change her behavior so that she doesn't commit serious crimes again in the future. If we could answer that and measure that, that would be this is a really complex tool. So if you think about it, we need to be able to measure, we need to be able to allocate police resources equally across New York City so that there would be as many SWAT teams up in the Bronx as there are in the East Village, as there are in, I don't know, some area like Clinton Hill in Brooklyn, so that should Brisha be at any one of those places and does something bad, somebody can catch her, and we can actually measure that outcome. Think about how complex that is, right? So what this thing actually gets good at measuring is who is more likely to be convicted. And when we ask that question, and we know that that's what the system's telling us, the answer becomes totally clear. Of course it's biased, because that's what it's actually measuring. It's not measuring this thing we think it's measuring. This is relevant not only for ethics questions, but for like any machine learning product that you're building. Because you often think you're trying to optimize for X, but when you reduce it down to the simplistic proxies that are required to do quantitative work, they're often a little bit different than what you think. And that can lead to like skewed business results as well as ethical pitfalls. So back to the data collection thing, this is not unique to recidivism risk use cases. This is a recent book published by Virginia Eubanks about using machine learning tools in other sensitive social use cases. Her example was in Allegheny County in Pennsylvania, where they were trying to use algorithms to identify children in homes who might be victims of abuse. And here, the risk came in not in the middle of the algorithm, but again, how the data was collected. So in the US, as we know, this was public health data programs. And the people who use public programs tend to fall under in a certain socioeconomic class. So rich people go to private doctors, poor people go to public doctors, and therefore the tool was very skewed in making its prediction towards a certain subsection of the community, because those are the people who go to public health facilities. Nothing about the algorithm, more about the data collection. So once we've got our data, we then move on to processing it. So processing it means sort of representing it. Remember with the polar coordinates versus the Cartesian coordinates, so it will work well for an algorithm. As I mentioned, often when we're trying to figure out what those features are that are going to matter, a data scientist would work together with somebody in the business who sort of knows their way around the world so that they can interpret the data accurately. Those people that they work with are humans, and those humans come with biases. So it's not like when we're analyzing which data might be like the data that's going to be relevant for our predictions, it's not a process immune from input and bias. So naive attempts to say, okay, great, we want to rid our data set, skim away all of the things that we think are sensitive in society. So we don't want our predictions to be based upon gender. We don't want them to be based upon race. We don't want them to be based upon marital status, let's say. So the first thing we'd say, all right, let's go into our database. Let's find the column that has gender, and let's just erase it. So it's not going to make an impact on our prediction. So this is akin to something that actually worked in the physical world in the 1970s, where they noticed that there were systemically many fewer female concert mistresses in orchestras than there were men. So they actually just they changed around the protocol for auditioning, and now I think it still holds. Now, when you go, if you've gone to Juilliard and you're an excellent violinist, I'm a crappy amateur violinist. I do the best I can. When you go, the person who's auditioning you doesn't see they can't see you. They can only hear you. And when they made that shift, so they had blind auditions, it led to a total, there was a statistically significant uptick in the number of women who had concert mistress positions. So that worked in the physical world. It can be tough when we get into the data world. So let's imagine we're saying we don't want race to impact our predictions to decide who gets a loan in Chicago. So we remove it from our database, but this is a lovely map that shows the distribution of different races across the Chicago metro area. The magenta is where white people live, and the sort of turquoise is where black people live. So note, if you were to leave Canadian, zip code, in your, Canadian postal codes are much smaller than American zip codes. So privacy issues when you retain your postal code in Canada are much different, much more granular, and much more subject to the risks of anonymizing your data and thinking that it's safe for privacy reasons, but it's actually not. They're really small, granular domains in Canada. So, side point. So say you keep your zip code in, but you remove your race, you could see that you're proxy encoding for race if you keep that in. So it's really thorny. You can't just sort of remove a column and imagine that you're good. It takes a lot of subject matter expertise analysis across various columns to know which ones are going to be relevant. Going into data privacy, it was a little bit of a preview for this next slide. You might say, all right, we also want to protect people's information, so we want to have the minimum data necessary to do a task, because if we keep things minimum, I have some friends in the audience that do a lot of work on information governments. The less information you have, the better, because there's going to be less sort of exposure if something bad happens. So that holds when what we're interested in is the value of the data, but it shifts around a lot when we move into caring about aggregates and caring about sort of like stats as opposed to caring about individuals. Because, as I just mentioned, with those postal codes versus zip codes, right? If you combine my postal code, my gender, and my age in Canada, you probably will know me. If you do that in the US, you'd have a lower likelihood because you got many more people in one zip code. So we actually have to think about the structure of the stats in providing stronger privacy guarantees when we move into this world. When you're doing data processing, I mentioned earlier on in supervised learning that we want to have multiple examples of the right answer, right, the right data point to train our future predictions. So that's called labeling our training set. So some of these uses are super benign. So my former colleague Hillary Mason used to walk around New York and take pictures of things. And I love that actually the New York City subway system would often come up as gates or like correctional institutions by our classifier. We'll talk about edge cases in a different talk. But there's certain labels. I bring this up just because, you know, if it gets it wrong and says it's a gate, we're laughing, right? We're not upset. So there's certain instances where these labels can be kind of frivolous and they're fun. There's others where the labels can be more detrimental. So there's a couple of papers that came out, I guess this was in early 2017 or late 2016. These are by some Chinese data scientists who claimed that their deep learning algorithms were able to predict who would be a criminal more accurately than judges. So if you look at those two lines, the criminals are in one row and the non-criminals are in another, right? So pretty easy for us to identify which they might be. The argument that my friend Blaise Aguera made in his excellent article on Medium about this use case was that we're interpreting this incorrectly. This is not that the algorithm's super smart and is using physiognomical traits to predict if you're going to be a criminal. It's that judges in the past have made calls, sometimes baking in their prejudice as to who was an upstanding citizen and who was not. And these algorithms are becoming launderers of human prejudice, right? So the accurate representation is that they're baking in our judgments as opposed to these are somehow objective systems that are removing bias from the judicial process and equation. They have another article that makes a very similar argument related to gaydar. So this was from our dear friends at Cambridge Analytica, who after having a great impact on the American political system went on to claim that they could build tools that could predict somebody's sexual preferences from their physiognomy. My friends showed how this actually was not encoded by anybody's ingrained physiognomy, but rather the same person could pose and perform the social conventions that we have to be a heterosexual male or female or a homosexual male or female, and that these systems were picking up indeed on features within the data that socially signified sexual preference, but that they had nothing to do with one's ingrained, inborn physiognomy. So the moral of the story here is that we have to be careful in the scientific and the engineering community in making statements that lead us to believe that algorithms are somehow more objective than we are, right? They're actually just baking in a lot of the same social conventions or biases that we work with. All right, another example in our bias greatest hits comes from imbalanced classes, so minorities represented in your data set. So it's a common technical problem that anybody doing data science in the wild faces, that you've got a ton of examples of one class. So like, in this example, this was, is this checklist compliant or not? And you've got like 99% of the answers are yes, and you've got a little 1% set that are no. And to be able to like solve this problem technically, you'd want to have sort of 50-50. So you've got a lot of examples of the one and a lot of examples of the other, so that your algorithm can pick up on those differences. When we face this same problem in the social world, things can get tricky. So sometimes, say, we're building out an algorithm where we're trying to provide the right offer for a marketing offer, let's say, the right offer to the right person. And we've got tons of examples based on people's past behavior of like what rich white dudes like, and like 5 examples of what, I don't know, let's say rich African American women like. So if you note, your algorithm, the size of the error goes up exponentially the smaller your sample size. So it does really well on areas where you've got a lot of examples of the type of population you want to know a lot about, and it like does really badly close to random on the minority population. So that's just the inherent statistical problems we face in certain data set sizes. Example of this in sentiment analysis realm. This comes from my former colleague. Slightly different, but variations on a theme. So our question here is, we want to identify negative statements that people are saying about our brand so that we can have feedback and modify our marketing programs to address those claims. So it happens that white males, well, not white males, men, sorry, I was reading the Homer Simpson thing. Men as a whole tend to use more strident language on Twitter. So they're the, like angry jerks are either bots or dudes. These algorithms aren't that smart. They do really well with strident language, right? So if you're like, this sucks, they're like, negative sentiment. And if you're more nuanced in how you critique something, so this might actually not be a great product, they're gonna have a harder time figuring that out. So because the tools aren't that great, they're not that smart, they'll have a higher likelihood of finding the dude's comments, and therefore, from a business perspective, those men will end up attracting more attention from the brand as they try to modify their programs to address any consumer concerns. One more example in the NLP space. So this one's pretty famous from some researchers at Microsoft a couple years back. So as we move from, humans pick out the features to we take in a bunch of data, represent it as a string of numbers, and let the neural networks do their thing. We also invite, because we need a lot of training data to get these things to work, a lot of the patterns inherited in our data from the past. So when we build out these embeddings, are basically just math representations of language and words. They've been used to do what we call word algebra. So you'll say, all right, plot man. Let's just go back to the picture. So we'll say, as man is to woman, so king is to what? Okay, and the computer is able to basically measure that distance and then measure that distance and use that measurement as its answer. So these folks at Microsoft Research did some analysis and found that, all right, did that, totally cool, socially neutral. Maybe in the past it had some ramifications, but doesn't really for us here in America these days. But then they also found that it came up with things like man is to computer programmer as woman is to homemaker, and black male is to assaulted as white male is to entitled to. So again, this is not the fault of the algorithm. These were lying in the data. The algorithm picked them up. But I was with some folks yesterday at a think tank hosted by Adobe, and what drew my attention to this is that this isn't just something that's out there in some tool. These are often in the open source tools available from Google that a lot of people working in startups and working in companies that can't build this from the ground up are using. So it's not just sort of a one-off thing. You might be using a tool that has this at its basis today if you're using Word2Vec NLP algorithms at all. So it's important because of this value chain of products and data that we really sort of think back to the roots of where this might start, because it can creep up on us if we're not careful. This is just a way to conceptualize this. I like to think about this effect as what I call the time warp of algorithms trained on historical corpuses. So we have evolved as a society from the days of Mad Men, where every woman was expected to be a homemaker. However, we make a mistake in assuming that AI is super future forward, futuristic, fancy stuff, as opposed to, if we're not careful, potentially the most conservative technology we've ever worked with, because when we have to dip back into historical data sets in order to get these things to work the way we'd like them to, we end up finding and recovering past social conventions and sort of pushing them up into the future again. For me, this reminds me of when I, as a hopefully now mature, calm 34-year-old woman, when I go home and spend time with my parents, the last time I lived with them was when I was 18, at which point I was a completely neurotic freak show teenager. And they still know me then, right? That's the last time they've lived with me day in and day out. And so, they expect that because they haven't been with me as I grew and processed over the years. And I go home and I'm like, oh my God, I thought I was beyond this, right? But I'm facing the reflection of what I once was and what I was in their eyes. And I actually think that experience is quite similar to what's happening at scale in society with these algorithms. All right, 2 more things, and then we'll move on to the so what. There's ethical and design implications on the front end. So for those of you here who are working in UI, UX and thinking about how we process the output of algorithms. So it need not be, remember we have the whole 0.88% likelihood to convict, and we turn that into the risk score. So there's choices that designers can make as to how they present the output of an algorithm to a user. It could just be that it's an 8, you get nothing more. Or it could be something like my friend David Madras is working on, where if it's above a certain level of confidence, you sort of go for an automated result. If it's below a certain level of confidence, it might be don't do anything. And then if there's this range of uncertainty, you can present something to the user that's like, we're really not sure here, requires further investigation. And that's just it's a little bit more of a thoughtful design choice, but it shifts around the experience that the user of the system has, in particular if it's to support a decision as opposed to sort of just be fully automated. I'm gonna skip over that. Okay, so morals of the story. I hope I've convinced you that this is not just about models. It's always more than that. And we have to think about our open source tools. We have to think about where data comes from. We have to think about what we can measure and what we can't measure. So it's really a holistic process. I hope I've convinced you that proxies are powerful, but they're tricky, and we have to think really hard about what they represent. And finally, that bias creeps in all sorts of places. So in our training data, in the way in which we go about selecting features, if we do that with a deep learning style or a more classical stat style, how we go about selecting target variables that matter, and then our UX and UI. All right, so what can and should we do? So we'll start briefly with some of the cool technical solves that are out there in the research community today. So Bullock Bossi at Microsoft didn't just stop at recognizing that word embeddings have bias. He went further and tried to do something about it. So they had a really cool solve. So they said, why don't we plot gender on the x-axis, right? So words that are associated with women, words that are associated with men. And then above the x-axis, we've got words that are socially sensitive. So words that we're uncomfortable when they're associated with gender. And below, we've got words we're comfortable with. So it's totally cool to say that girlfriend is a she, grandmother is a she. And it's totally cool to say that a chap is a dude, is a he. I guess I used a dude. That's funny that I said that. But then there's other ones that make us uncomfortable. So what they said is, for all of the words below, we're going to let them be. For all of the words above, we're going to sort of collapse them down to that middle axis and make them gender neutral. So they went in and they sort of tweaked things around to try to debias it for these references. This notion of finding a way to represent your data so that it leads to fairer outcomes has variations across the fairness community. So I work very closely with a man in Toronto named Richard Zemmel. He's at the University of Toronto. And he, together with his wife, Tony Patassi, a woman named Cynthia Dwork, was at Microsoft at the time. Where's Cynthia now? Harvard? Yeah, since she's at Harvard now. They did some work all the way back in 2013 that kind of went on deaf ears for a while and is now starting to really take off in thinking about fairness. So equal treatment to different sensitive populations, minorities, as a representation and optimization problem, where you can say, all right, here's our task, predict whether or not somebody should get a loan. Let's reformulate our data set so it still keeps and preserves all the information we want to make that prediction, but obfuscates the aspects that are sensitive. So it's a way of solving that problem where zip code and, let's say, race are correlated by using pretty complex statistics and probabilistic techniques to try to sort of decorrelate those things while still retaining the power of the tool. There's ways to do post-hoc analysis. So as opposed to going in and fixing how you represent the data, you can do something afterwards to try to understand how the model is working. So this is one where you've got your data, put it in a model, gets an output, and it leads to some conclusion. You take your data, modify it in some way, put it in and through, and then measure not at the base of the algorithms, but how are those two things different now that you've transformed it. This is some work from a former colleague of mine who's going to be at MIT next year. He was at Google Brain for a little bit. Other types of post-hoc analysis are trying to figure out that whole explainability issue. So what actually is leading to the results? So here, we've got this weird picture of a dog with a guitar, and we're trying to figure out what aspect of that image, again, was leading to the algorithm to do what it does. And we'd want to do this to be able to solve problems if there's bias issues. So what these guys do is they say, as I mentioned, the functions when we get into deep learning are sort of twisting and turning. But they say, all right, let's zoom in to one small portion of our function, and in that little area, pretend it's linear, and sort of analyze it with our microscope in that little area to see if we can figure out what's impacting it there to make inferences about what are the sort of features that matter. So it's post-hoc. It's like you do your thing and then you sort of play around with it to see what works. So this is just a little bit of a sample of some of the technical things people in the community are working on. And then there's also governmental policy and then internal processes we can think through. So one of the first things is, and this is from Kate Crawford, who's based here in New York. She leads an institute called AI Now. It's working on these issues. She gave a great talk at NIPS this December out in California about bias, and had a great slide where she showed how the various communities use the term bias differently. So for the data scientists in the room, in your mind, you're probably thinking about nature, properties of data, how your curves are fit, et cetera. For the cognitive psychologists and honestly laymen in the room, we're thinking about bias in different ways, where it's like judgments that we might make, ways in which we might interpret things differently, prejudice and inherited traits in society, et cetera. So there's a first step that is like we need to make sure that when we're talking with one another, we're actually communicating and we're not using terms in different ways. There's some cool policy work afoot. I'm working together with this lady pictured here, who leads fundamental research for a bank called RBC. We're trying to lobby the Canadian government, who's put $200 million into AI research in Canada, to withhold future funding unless 20% or 15 to 20% of the work is devoted to privacy, security, and fairness. So this is a powerful people in the community who are trying to impact where money gets spent to enforce research on these really hard problems. And then there's regulation. So regulate fairness, accountability, transparency, and ethics. And let's not forget privacy and security. So there's been some regulations that are already in play. There's a regulation coming out in the European Union, the General Data Protection Regulation, in 25 days from today. It's tricky because they've said that every consumer deserves a right to an explanation for why an algorithm provided them, allocated them some product, or didn't allocate them in a certain way. It's led to a lot of interpretation confusion in the various sides of the community. So on the top, you see people like Pedro Domingos from University of Washington saying that, in standard Twitter outlandish speech, that deep learning is going to be illegal because it's not possible for deep learning for us to explain why they do what they do. I thought that was kind of the case, and I was shopping it around, and I gave a talk at Harvard where there was a guy who works at PwC Europe who wrote me the following LinkedIn messages, who's like, look, I talked to my lawyers and they all think it doesn't go that far. And basically, if you read this text, he's saying an explanation is like I've used an algorithm. So on the one side, we have a strict interpretation that says no algorithms are possible, innovation is stifled. And on the other side, we've got you can legalese your way out of this easily. So the question is, what is meaningful transparency? What is meaningful explanations? What would satisfy the psychological needs of people impacted by these tools? So Julia Powell's over at Cornell Tech wrote a good article in the New Yorker in December about the New York City actually's attempt to put in some sort of standard related to the use of algorithms in police use cases here. And she said it was totally flawed because they took transparency a little bit too far. So it was like, all right, we want to be able to disclose the source code for analysis by third parties, but like that's not meaningful to a lot of people. So, and also, I was talking to somebody about this earlier on before we got started. They might disclose sort of metadata around the use of the algorithms, but not all the secrets and all of the bias that went into selecting features, et cetera. I think there's a lot of dangerous talk that we read about in the media where people say, well, why are we so concerned about making algorithms transparent and explainable? Humans don't know why they make decisions either. So we are hampering innovation by placing machines at higher standards than we do humans, and we should just sort of accept that this is the way things work, and eventually we'll get used to it, and everybody will catch up. And I find, yeah, it's accurate that we have a lot of complex stuff going on when we make decisions too, but it's certainly from, in my perspective, being a software company that works with large consumer enterprises, it doesn't provide the head of privacy or the head of legal any comfort that they are going to satisfy their compliance requirements if I give arguments to the tune of, well, humans don't really know how they do stuff either. So these aren't useful arguments. So we have to recognize that we want to know why things occur, but that I believe our focus is too narrow, and we tend to want to ask questions of cause to systems that are fundamentally about correlation. This is a picture of David Hume, my namesake, who wrote a lot of articles, wrote a lot of essays about this in the early 18th century. So I think there's an opportunity for us to think about how to provide meaningful transparency using the arguments that are proper and appropriate for statistical tools. So I really like this precedent from a judge from 2012. His name's Andrew Peck. The question at hand was, can lawyers, actually this will be familiar to some friends in the audience, can lawyers use machine learning tools to identify documents that are relevant for a lawsuit or not? Is it acceptable? And there was a lot of arguments against that because the community was uncomfortable, just like we are with self-driving cars and a lot of new technologies, with sort of the changes that this might mean to their ability to find evidence that was relevant for legal cases. And he said, I do want to feel comfort that enough evidence has been produced so that I can make a good judgment on the case. So I gotta know the facts to the best of our ability. But he says, like, I'm not as interested in how the model works. So let it be a black box. What I want to know is if there's enough recall and precision. So I want to know if we've got a good expanse of the right evidence across the set. And therefore, it's much more focused on the distribution of outcomes that the system has produced, and then sort of documentation of how the process worked, that there's been good quality control, et cetera. So there is documentation, but what qualifies as, like, is this working or not, is specific to the task. So we're interested here in having enough evidence to solve something, and it has to do a lot with the distribution of outputs. So my thinking, and this is all a work in progress, so I would love if we maybe take a break for question, maybe we can even talk about this slide, is like, what would an outcomes-oriented framework for meaningful transparency look like for an organization? So my take is, you gotta have somebody who's responsible for it. If you don't devote somebody full-time, it's never gonna happen. I think you have to start by stating the problem and the policy for the outcomes you want to achieve. So if you're, say, Capital One, and you're thinking about fair allocation of loans across a population, the CEO has got to make a call on how fair he or she wants to be, and has to own that accountability. Because as a technologist, even though we think about having an ethical code for data scientists, when push comes to shove, you're not always empowered to own that kind of responsibility and liability in business, but people up high are. You need to spend time with the users impacted by your system, so not do this in a vacuum, but really know Brisha, know what would happen to her if something went wrong, know how she works with your tool. I like these ideas of pre-mortems, so not a post-mortem, we just did this, what went wrong, but starting off and imagining all of the bad things that could happen before you launched a product and working backwards to say, all right, what do we need to do so that that doesn't happen? As I mentioned when I did the things, it's really important to map the entire process of going from data to providing value to a user or like a decision to a user, because it's not just in the algorithm, it's across the board. To get really clear about your proxies measure and don't. I think there should be, in various phases, auditing for fairness, privacy, security, et cetera, in particular during the QA and testing phase of building a product. And then testing for interpretation pitfalls is basically, so when you've got a human who's using this, going back to that I don't know, like how are they engaging with it? What are the confusions? Where do their brows furrow? Because they're not really sure what to do with the tool. And then document, learn, adapt, change, right? So you're not going to get it right on the first go, but need to sort of keep adapting in the future. So this is incomplete. Up there to get a lot of feedback, so I'd love to engage with it. And my missionary message is that we need to admit to the realities in our society, not think that they're, not espouse these polite fictions that guide our social engagement, because if we do, we can rewrite our future. So thanks.